Professor, you can start.
Thank you. Let us start. So we continue our discussion on toric varieties. I keep the previous notation from the previous lecture, so I will denote a given toric variety by X. It contains the given algebraic torus T as the open orbit. For any other orbit, say Y in X, we have the simple open subvariety X sub Y, consisting, which is the union of all orbits containing this Y in the closure. And this simple open subvariety actually coincides with the affine, with the canonical affine B chart, open B chart, which I denoted previously by X Y naught in the general case. Because what is this guy? This open B chart is obtained, if you remember, from this simple variety by removing all B-stable, all colors, you may say, by removing all colors which do not contain Y in the closure, which do not contain Y. But in the toric case, there are no colors, so there is nothing to remove. This means that this simple toric variety coincides with this affine open B chart. In particular, it is itself affine. So any simple toric variety with a unique closed orbit is affine. And the coordinate algebra, its coordinate algebra we can write it down because we know what is the coordinate algebra of this open B chart. It consists of all regular functions on the open B orbit, which have non-negative vanishing, which have no poles along B-stable divisors contained in this simple variety. In our case, the open B orbit is just T itself. And this function, this algebra of regular functions, is spanned by all monomials, by all Laurent monomials, which are the same as B semi-invariant functions on the open orbit, F sub lambda, which do not have poles along T-stable prime divisors contained in this X sub Y. We know that this means exactly that the eigenweight lambda belongs to the dual of the cone corresponding to this orbit Y. And of course, it is a lattice vector. So it belongs to this semigroup of lattice vectors in the dual cone. And we know by Gordon's lemma that, so this algebra is actually the semigroup algebra of the semigroup. There is a concept of a group algebra. This is an extension, a semigroup algebra. So it is spanned as a vector space by semigroup elements. These lambdas are in a one-to-one correspondence with F lambdas, with Laurent monomials. And the multiplication of these basis elements, basis vectors in the algebra is given by the multiplication in the semigroup, that is by addition of lambdas in the additive notation. So this semigroup algebra, we know from Gordon's lemma that the semigroup of lattice vectors in the dual cone CY check is finitely generated. Let's pick the generators, a finite set of generators, say lambda 1, lambda m. Let them be generators of the semigroup. Generators of Cy check intersect with lambda. And the respective eigenfunctions, the respective Laurent monomials generate this algebra. So this algebra is finitely generated, of course, and it is explicitly generated by these Laurent monomials. So the coordinate algebra of an affine toric variety, of a simple toric variety, which is affine, is given very explicitly. It is generated by very explicit Laurent monomials in coordinates of the on the torus T. Let me give you some example. For instance, in dimension 2, we can take a cone something like this. For instance, well, I don't know, let it be like this. So this will be the, excuse me, thinner. This will be, say, the origin. One ray like this. Okay. The other ray like this, maybe. So this is the cone C sub y. And the dual cone, let me put it in yellow. Well, not maybe in yellow, in blue, for instance. It looks like this. So, of course, the dual cone sits in the dual vector space, but for convenience, I will draw it at the same picture. So the rays are these. This is the first ray. This is the second ray. So this is a dual cone. Cy check. And the lattice vectors in this dual cone, let me mark them by dots. So the origin, of course, and the other vectors. So there are plenty of them here, here, here. I don't want to draw all of them, but just some. And so on. Maybe yet another row. These are the lattice vectors, the elements of this semigroup, Cy check intersect with lambda. And the generators of this semigroup, of course, you have to take primitive lattice vectors, indivisible lattice vectors on the rays. They cannot be excluded. So this one and this one. They generate the cone, Cy check, but they do not generate the semigroup. To get the full set of generators of the semigroup, you have to add this vector and this vector. So these four vectors already generate the semigroup of lattice vectors in the dual cone. And if you choose some coordinates on the torus, if you choose the basis in the lattice lambda, you can express these vectors in terms of this basis as integer linear combinations. And you can write the respective Laurent monomials in coordinates on T. And these Laurent monomials generate the coordinate algebra of this simple affine toric variety. You can write the relations between these monomials coming, of course, from relations between vectors in the semigroup. So sums of some of them are equal to sums of other vectors. So the relations are of binomial form. This algebraic variety, this affine algebraic variety, can be given explicitly in terms of generators and relations of its coordinate algebra, or in other language in terms of equations in the ambient affine space. In this case, in this example, the ambient affine space will be of dimension 4 because there are 4 generators for the coordinate algebra. But the relations between the generators give us an affine subvariety of codimension 2. So this is just an example. So I said that any simple toric variety is affine, and the converse also holds. So conversely, any affine toric variety is simple. This is actually a very general fact, that if you have an affine algebraic variety acted on by a reductive group such that there is a dense open orbit, then the closed orbit is unique. But I don't want to use this general fact to prove this statement. Yes.
I missed that.
Excuse me? What did you miss? The last statement.
What is the general fact stated?
Let me repeat. The general fact, which I won't use, so I don't write it on the whiteboard, is that if you are given an affine algebraic variety acted on by a reductive algebraic group in such a way that there is a dense open orbit, okay? Then the closed orbit on this variety is unique.
Oh, this works for any reductive group and any
reductive group acting on an affine algebraic variety with a dense orbit. Yes. In this case, the closed orbit is unique. But in our situation, we work in the spherical case, now even in the toric case, but we shall prove this fact later for spherical varieties. And even a more precise statement, we shall give a criterion for affinity of a spherical variety, which in particular implies that this variety is simple. So we shall prove this statement later in general, a bit later in general, for general spherical varieties. And now I leave it without proof. So to conclude our discussion, we have the following. So simple, which is the same as affine, toric varieties are in a one-to-one correspondence with pointed polyhedral cones in the vector space spanned by the dual of the weight lattice, as usual, in this vector space E. Well, I should say colored cones, but in our case, in the toric case, there are no colors. So the color set is empty, and I have just to look at the cone. A colored cone is composed by two data: a cone, pointed polyhedral cone satisfying some conditions, and the set of colors. In our case, the set of colors is empty. And one of the conditions on the cone, that its relative interior intersects the evaluation cone, in this case, it is trivially satisfied because the evaluation cone is the whole vector space E. So a simple toric variety or affine toric varieties, which is the same, R is just in a one-to-one correspondence with pointed polyhedral cones in this vector space. Okay. As for general toric varieties, so arbitrary toric varieties, again, it follows from the general theorem that arbitrary toric varieties are in a one-to-one correspondence with colored fans. In this vector space. But in the toric case, again, we can forget about colors. So we can remove this word colored from the definition because the set of colors is empty. And what is a fan in the vector space E? It is just a finite collection. So let me explain what is a fan. It is just a finite collection so fans are finite collections of pointed polyhedral cones intersecting along their faces, so their relative interiors should not intersect. This means that the cones may intersect only along faces, intersecting along their faces. And this collection of cones should be closed under taking faces. So this is what a fan means. I just take the definition of a colored fan and adopt it to the toric case. There are no colors, so any face of a cone intersects its relative interior intersects the evaluation cone, so any face is also in the fan. And any two cones may not intersect in their relative interiors. So they cannot intersect in their relative interiors, so they intersect along faces. This is the classification of toric varieties in terms of fans. And also geometric properties are visible from this combinatorial data, like fans. The orbit set, the closure ordering of orbits, it is just because it is so in the general spherical case. And in particular, we had the completeness criterion. So in the toric case, the completeness criterion says that a toric variety X is complete if and only if its fan covers the whole vector space E, so-called complete fan. In the spherical case, the criterion is that it covers the evaluation cone, but here the evaluation cone is the whole E, the whole vector space. So maybe the most basic example of a complete toric variety, let me give you just an example, is the projective space. Let's consider this example in detail. So let X be the n-dimensional projective space on which the n-dimensional torus T acts in the following way. So a point with projective coordinates, maybe I should better switch to the next line, somewhere here. So a point with the projective coordinates x0, x1, etc., xn maps under the action of an element t in big T to the point, so x0 is unchanged, and other coordinates are multiplied by coordinates of t. So t1, x1, etc., tm, xn. Just the usual, the natural action of an n-dimensional torus in the n-dimensional projective space. You may first consider the action of the n-dimensional affine space. Just the torus acts by diagonal matrices on the n-dimensional affine space, and this coordinate x0 on the affine space, it is non-zero. It is equal to 1, for instance. And this action extends to the action on the whole projective space by this formula, the very natural action. So let us describe the colored fan in this case. This projective toric variety, the projective space X, is covered by n+1 open simple affine toric subvarieties, just affine charts. So X is the union of xi's, where each xi is given by an inequality that the ith projective coordinate is non-zero, and it is just an affine chart. It is isomorphic to the n-dimensional affine space. And this simple toric, this affine toric subvariety, which is simple also, as we stated before, gives rise to a cone Ci in the vector space E. Let us describe this cone. So look at the coordinate algebra of this open subvariety Xi. So it is generated as an algebra by affine coordinates on this Xi. The affine coordinates are the following: x0 over xi, x1 over xi, etc., xn over xi, where of course we skip the ith fraction. Xi over xi is just the unit element. It is not included in the generators, in the set of generators. And the weights, eigenweights of these functions with respect to the action of t are the following.
Yes. Professor,
yes?
you write xi covers x. Is that means does that mean that xi is a simple T variety?
Yes, xi is a simple T variety. Xi is an affine T variety, and I claimed before that any affine T variety. But in this case, I mean, it is visible that it is simple, because what are the orbits? It is easily seen that the orbits are just given by taking some coordinates to be equal to 0, and the other coordinates be non-zero. So an orbit is distinguished by saying which coordinates are 0. So the closed orbit on xi is just a fixed point. It is given by the inequality that xi is non-zero and all other coordinates are 0. So it is easily seen that it is the unique closed orbit in this affine space. But of course, the simpleness follows from the general statement on the previous page. So what are the weights? So you see that the weights can be seen from this formula. So when you look at the eigenweight of a function, you have to act on the argument of this function by the inverse element by an inverse element of the group. So you have to act by T inverse and look what happens to these functions. So the weights of x1, etc., xn are minus epsilon 1 minus epsilon n, where epsilon i's are basic characters of T. And the weight of x naught is just 0. So you see that the weights of these fractions are the following. So here you have epsilon I, and here you have epsilon I minus epsilon 1, etc., epsilon I minus epsilon n. This is for non-zero I. For non-zero I. And if I is 0, then we have just, we don't have this, we have only these fractions. If I is 0, we have just minus epsilon 1, etc., minus epsilon n for I equal to 0. These are the eigenweights of the generators of the coordinate algebra. Okay? And as we have seen before, these eigenweights span the dual of the cone Ci. The dual of the cone Ci. Okay? And this, well, they even span the semi-group of lattice vectors in this dual cone. But in particular, they span this dual cone. And this implies that the cone Ci itself, so it is the dual cone to this guy, to the cone spanned by these vectors. You can easily compute the generators of this cone, dual to the dual. It is just the cone. Again, maybe I will move to the next page, to the next line here to have more space. So Ci is spanned by the following vectors: minus epsilon 1 star, epsilon 1 star, epsilon n star are the basis vectors of the dual basis in the dual weight lattice. Yeah, they are dual to epsilon 1, epsilon n. So minus epsilon 1 star, etc. On the ith place, we have epsilon 1 star plus, etc., plus epsilon n star. This we have on the ith place in this list. And so on. Minus epsilon n star at the end. So the cone spanned by these generators is the dual one to the cone spanned by these vectors. Because actually these vectors form the dual basis to these vectors. So these vectors, rewritten in a proper ordering, form the dual basis to these vectors. So they span the dual cone. This is for I non-zero. And for I equal to 0, we have to take these vectors and take the cone spanned by the dual basis of these vectors. So we have C naught be the cone spanned by minus epsilon 1 star, etc., minus epsilon n star. Since these simple open subvarieties cover the whole X, their cones, the respective cones Ci, so all these cones and all faces of these cones form the fan of this projective space considered as a toric variety. And it is easy to see that all these cones cover. So let me write somewhere here. So C naught, C1, etc., Cn cover the whole vector space. Let me give you a picture, for instance, for n equal to 2. If n equals 2, then we have the following picture. So what do we have? We have the cone C naught spanned by the vectors negative to the vectors of the dual basis. So it is something like this. Yeah, something like this. But maybe let it be in black. So this ray minus epsilon 1 star, and this ray minus epsilon 2 star. Okay? The cone C1 is obtained by replacing minus epsilon 1 star with this sum, epsilon 1 star and epsilon 2 star. So we have yet another ray, this one, this one. This ray and this ray will span the cone C1. So let me indicate here. So this is C naught. This is C1. And the last cone C2 is spanned by minus epsilon 1 and this sum instead of minus epsilon 2. So C2 is this cone. So these three cones of dimension 2 and the three rays, which are the faces of these three cones, and also the zero-dimensional face, just the origin. These 7 cones compose the colored fan, the fan of the projective plane of P2. So there are 7 orbits, and the orbits correspond to these cones and their faces. And of course, for general n, the picture is similar, but I just cannot draw it explicitly on the sheet of paper. So you can imagine the same thing for general n. This is the simplest example of a toric variety, of a complete toric variety, just projective space. Well, I will stop now discussing toric varieties. As I said before, toric varieties are so definitely they deserve a special lecture course. It is a very nice theory of them. But for me, in my lecture course, it is just a particular example of spherical varieties. So my aim was to describe how the theory of toric varieties fits into the general theory of spherical varieties. maybe I just give you a couple of references. If you are interested in toric varieties especially, then maybe some good references for you will be the following. References. Maybe the starting thing is the book of Fulton. The book to start with is of Fulton, by Fulton, Introduction to Toric Varieties. It is quite elementary and comprehensible. And there is a more modern and more extensive book by 3 authors, David Cox, John Little, and Henry Schenk, called named just toric varieties. Toric varieties. It contains much more material and many references. So if you want to go to this theory deeper, then maybe after the book of Fulton, you can take this one. It contains all up-to-date information about toric varieties, which exists for the moment. And maybe I finish my discussion on toric varieties just with a couple of exercises. So the first one. Will be to describe the fan for the following toric varieties. The first example will be the product of 2 projective lines, P1 cross P1, which is a toric variety for the 2-dimensional torus, K cross to the power 2, which acts on P1 cross P1 in the following way. So maybe I would even write it like this: K cross cross another copy of K cross. So which acts obviously here. So the first copy acts on the first factor, and the second copy acts on the second factor. And the action of K cross, on a projective line is taken from the previous example. So a point with projective coordinates x0, x1 is taken to a point with coordinate x0, t x1. Under the action of some t in K cross. Okay, so this is the first example. Compute the colored fan. The first exercise, compute the colored fan for this 2-dimensional toric variety. And yet another 2-dimensional toric variety is the blow up. So X is the blow up of one of the fixed points in P2 For instance, you may take a point with this projective coordinates in P2. It is a fixed point under the action of t in the previous sense. In this sense, and when you blow up this fixed point, then of course the action of t lifts to the blow up, and so the question is to compute the fan for this projective toric surface. This is the first example, the first exercise, and the second exercise will be about invariant valuations, t invariant valuations, exercise 2. So let us take a t invariant valuation corresponding to an arbitrary lattice vector in the dual of the weight lattice for any v in lambda star. First, prove, so for any v in lambda star, prove
will this lambda
lambda is the character lattice of the torus, the weight lattice.
Oh yes. Oh yes.
Okay, so for any v in lambda star, prove that, so recall that on the previous lecture, we associated a one parameter subgroup to any lattice vector in the dual lattice. So this curve this one parameter subgroup in T, this curve where the parameter S is sent to S to the power V, intersects the boundary divisor in the corresponding elementary toric variety corresponding to this valuation transversally. At the limit point, so this parameter S is a multiplicative parameter. It belongs to K cross, but you can tend S to infinity, and so the limit point. So when S equals infinity, the limit point will be not in the torus, not in the open orbit, but on the boundary divisor. So the exercise is to prove that this curve intersects the boundary divisor transversally at infinity, at S equals to infinity. So the picture is like this. We already seen this picture. So we have this one parameter subgroup. Yeah.
But what will happen if we can't solve all the exercise?
Excuse me?
Well, what will happen if we can't solve every exercise?
What do you mean by?
Well, if I have problems solving some exercise, what should we do? Well, I mean this.
If you cannot solve an exercise, well, I mean, first, those exercises which you can solve, I ask you to send me solutions to these exercises. So far, I've got just a few solutions, and there are already plenty of exercises. But even if you have maybe some partial solution, or maybe some questions on how to make the further step in solving a given exercise, you may address these questions to me, and I will give you hints how to proceed further. I will check what you did already, the steps which you succeeded to do. And if you have questions on further steps, I will give you hints, and maybe you then could proceed further. Okay?
Okay.
But but try to solve exercises, because it is important to get the material, to digest the material. It is important to try to do something by yourself. So let me finish with this picture. So we have this one parameter subgroup in T. And when the parameter S tends to infinity, so the exercise says that you will get a limit point. And this limit point will be on the boundary divisor of the corresponding elementary embedding. So I'm trying to draw this boundary divisor. Something like this. Prove that for any vector v in the dual lattice, the respective one parameter subgroup tends to a point at the boundary divisor of the respective elementary embedding of T. And this intersection is transversal. Just try to do it in local coordinates, because this xv is a simple variety. It is affine, and you can compute its coordinate algebra as we described on the previous page, on the first page. So you can compute the coordinate algebra given explicitly. And the second part of this exercise, part B. Part B is to prove that V is covered by the cones in the fan of X if and only if, again, let me move this picture. Okay, I think this will work. Let me move this picture somewhere here. So the second part of the exercise is to prove that the vector v is covered by this fan, by the fan of x, if and only if there exists a limit of this curve s to v as s tends to infinity in the variety x. Okay, so these are the exercises about toric varieties, and I will finish the discussion of toric varieties at this point. Any questions so far?
Well, part B, the right condition of part B is there exists a limit, right?
Yes.
There.
So the limit in an algebraic sense, because what is this curve? This curve is a map from k cross, from the punctured affine line to x. And when you speak about the limit, this means that this map from the punctured affine line to x extends to the point at infinity. So you add the point at infinity and you get the punctured projective line. I do not claim anything about the limit as s tends to 0. This is about minus v. This will be about the vector minus v, in fact. But when you add the infinity point, you get the punctured projective line. And the existence of a limit means that the map from the punctured affine line to x extends to the morphism to the regular map from the punctured projective line to x. This is what does algebraically mean that such a limit exists. Okay?
Oh, thanks.
Okay. So now let me finish the discussion about toric varieties and turn back to the general spherical case. I claimed just some time ago that affine spherical varieties are simple. Let me formulate a criterion of affinity for a spherical variety, which extends this claim, which makes this claim more precise. Let me formulate it as a theorem. So let X be a spherical G variety. So G is again a connected reductive group as before. So let X be a spherical G variety. Then the following holds. So X is affine if and only if several conditions are satisfied. The first one is that X is simple. Well, say simple with closed orbit, say Y. Let me denote the closed orbit by Y. So X in the other notation, X equals X sub Y. So Y is the closed orbit in X. This is the first condition. The second condition is that the cone, the cone, the other conditions, well, let me say like this, the other conditions say that the colored cone of X, of this closed orbit, if you like, has a special form. This means exactly the following. So let's consider the cone. So let's denote by C, by definition. The cone spanned by the cone of Y, the cone C sub Y, and all other colors, VD bar, over all colors. Not only those colors which contain Y, but all other colors as well. So we consider a bigger cone spanned by this guy and by all these vectors, even for those colors which do not contain Y. And the condition is that this cone is still pointed. The third condition is that the vectors corresponding to all colors are non-zero. So VD bars are non-zero for all colors. The fourth condition is that the colored cone CY of our simple spherical variety can be recovered from this big cone C as follows. So the cone C sub Y is the largest face of the cone C, whose relative interior intersects the evaluation cone. Of course, a colored cone must have this property, and so the statement is, the condition is that it is the biggest face of C with this property. And the last condition recovers the set of colors corresponding to the orbit Y. So the set of colors D over Y is exactly the set of colors whose corresponding vectors belong to this face. So in our notation, it is D intersect with CY. So this is the statement. So X is affine if and only if it is simple and its colored cone satisfies all these conditions. Maybe I will draw a picture and then make a break. So let me try to draw a picture. So we have the cone C. Let it be maybe in black. Well, let me start from here, maybe. Excuse me. And so let me start from here. This is maybe.
Well,
yeah.
But these five conditions are not equivalent, right? I mean, we should them
No,
come
no,
out.
no, no. I mean, affinity is equivalent to the union of all these conditions. So these conditions are independent. X is affine if and only if all these 5 conditions are satisfied. So let me continue trying to draw this cone. So I will try it to be of dimension 3. So this will be one face, maybe like this. 3 rays, 2 rays. Any 2 rays generate a face. So this will be another face, maybe even thinner. Let me try to indicate that this guy, even like this guy, this guy. So this is this cone C. Yeah. This is this cone C. And all colors are among generators of this cone. Some colors, and so we have evaluation cone also. We have evaluation cone somewhere here. This will be the evaluation cone. Let it be also of dimension 3 for the picture. Let me brush it as I usually do. So this is the evaluation cone. Okay, V. So the cone C is generated by all vectors in the cone Cy. So that Cy is the largest face of C and all colors. So that Cy is the largest face of C, whose relative interior intersects the evaluation cone. So at the picture, let it be like this. So we have this face. Let me again brush it with, say, with yellow. This will be my face. Excuse me. In yellow, this will be my face C sub y. No, it is not yellow. It is orange. Up to here. So you can imagine that this face of C intersects, its interior intersects the evaluation cone, and the whole cone C, the other part of the cone C, is somewhere above this face. And the evaluation cone is somewhere below this face. So this is the picture. This is, this face is Cy. And this Cy is generated by vectors from the evaluation cone, for instance, by this vector. This is a vector in the evaluation cone. Let me do it a bit more accurately like this. this one, and by some colors, for instance, this color will also be in the generators of Cy, and the other colors, for instance, this one, we have this vector, and maybe some other, I don't know which color to use, maybe black. They belong to C, but they do not belong to Cy, and they do not belong to this subset. So this is the picture, how all these things look like. So the evaluation, color, the affine embedding, the affine spherical variety is simple, and its colored cone is something like this one of the picture. So it is a face, the largest face of a bigger cone, spanned by all colors and some vectors in the evaluation cone, the largest face whose relative interior intersects the evaluation cone. So this is the statement of the theorem, and we shall prove this theorem right after the break. Now it is time to make a break for 10 minutes. So let's do it. And you may still ask questions if you have.
Yes, Professor. You at the start of today's course, you say that a generalized theorem say that reductive groups acting on affine variety almost has a unique closed orbit.
Not like this. Under the condition that it has a dense orbit, a dense open orbit.
I have some questions first. Do we need the reductive group to be connected?
No.
No. And do we need the dense orbit to be open?
A dense orbit is always open. This is a general property of orbits of algebraic group actions. Any orbit for an algebraic group action is open in its closure. This is a general property. I think so. For instance, in the Lie theory, when you consider actions of Lie groups, you may have something like dense enveloping of a torus or whatever, if you know these things. So an orbit may be dense, everywhere dense, but not closed, not open, I mean. For Lie group actions, this may happen, but for algebraic group actions, this never happens. Any orbit for an algebraic group action is open in its closure. So if it is dense, it is open. Okay. More questions? Well, I just turned off. Yeah. Mm-hmm.
A silly question. Well, no algebraic group can be complete variety, right?
Well, it depends on what you call an algebraic group. So in my course, by definition, I assumed that an algebraic group is an affine algebraic variety. It is the same as saying that an algebraic group is a closed subgroup in some GLN. So affine algebraic groups are the same thing as linear algebraic groups. But if you adopt a more general definition, if you just say that an algebraic group is an algebraic variety equipped with a group law such that the multiplication map and the inversion map are morphisms. Under this more general definition, there exist algebraic groups which are not affine. For instance, abelian varieties.
I see. Like the complex torus.
Exactly, like complex tori, yeah, like elliptic curves, yes. But I do not use this more general notion of an algebraic group in this course. Actually, I would say what is, well, maybe some philosophy around these things. The point is that, for instance, if you consider a complete algebraic group, then as people usually say, in this case, algebra is determined by geometry. This means exactly that on a complete algebraic variety, there exists essentially, if there exists any, there exists essentially a unique group law. So I mean, if you fix an algebraic variety structure on your complete algebraic group, then the group law is determined uniquely. The only thing you have to do is to fix the unity element, because of course you can shift everything. You can shift the group law by shifting the unity element. It is always possible, but it is the only thing that you can do. So the group structure is determined by the geometry of this complete variety. This is, for instance, for this reason, complete algebraic groups are called not complete groups, but they are called abelian varieties, because the variety structure determines everything else, all other things in this case. In the affine case, it is not the case. It is not so. For instance, there are plenty of algebraic group structures on an affine space.
I know this.
Yeah.
Even in the simple whole affine space, there are many different.
Yeah. So all unipotent algebraic groups have an affine space as an underlying algebraic variety. So this means that in this case the group structure is essential. If you are interested in algebraic groups, the group structure is also essential. Not only geometry, but also the group structure. This is one of the reasons why some people prefer to call only affine algebraic groups, to call them algebraic groups. And anyway, this is the convention for my lectures. More questions, comments, whatever?
Oh, another silly question.
Yeah, go ahead.
Is a complete algebraic group over algebraic closed field always abelian?
Yes. Complete implies abelian. Yes.
Oh, well, I think we need algebraic closed without.
Well, it depends again. I mean, it depends on what do you call complete. For instance, you may consider an algebraic group over real numbers. For instance, you may take unitary group. Yeah, the unitary group. It is an algebraic group defined over real numbers. It consists of complex matrices, but the algebraic group structure is defined over real numbers. If you complexify this algebraic group, if you consider complex points, then you will get the whole GLN of C. But the real points of this complex algebraic group, the real locus, will be the unitary group. And this unitary group will be compact with respect to the Hausdorff topology. Will you call it a complete group? Well, I don't think so, because in my feeling, completeness is a geometric notion. This means when you speak, at least when you discuss algebraic varieties, you have to turn to the closure, to the algebraic closure of the field of definition. So it is a geometric notion. But I mean, if you turn to a more general viewpoint, I don't know, if you consider schemes, group schemes, then maybe some peculiar things may happen about the definition of completeness in this case. And I'm not quite skilled in these things, so I'm not sure what about this more general situation. But yes, I mean, in the algebraically closed case, completeness implies that the group is abelian. This is for sure.
Oh, thanks, Professor.
You are welcome. Well, I see that we have just 1 minute left, 1 minute left for the break. So if you have more questions, still have some questions, then you may ask them. Otherwise, we can continue. Okay, well, let's continue. Let's go on with the proof. So we have to prove the implications in both directions. Let me start with the direction from the left to the right. So suppose that x is affine, and we have to check all these conditions. Okay? Since x is affine, it is determined by its coordinate algebra, and the coordinate algebra of x is decomposed as a direct sum of irreducible G submodules, which I previously denoted in this way, k of x sub lambda in brackets, where lambda are the highest weights, and let me denote by f lambda as usual. So the sum over some lambdas. Let me denote by f lambda as usual the highest weight vector in this irreducible G submodule in k of x of highest weight lambda, highest weight vector. It is a B semi-invariant function on x, well, B semi-invariant function with eigenweight lambda. And we want to understand which eigenweights correspond to regular functions on x. So the regularity condition means exactly that f lambda has no poles along all b-stable prime divisors in x. This means that the vanishing order along these divisors, the vanishing orders should be non-negative. So the condition is that, let me shift to the left, that Vd of f is non-negative for any b-stable prime divisor in x. But this vanishing order is exactly the same thing as the pairing of the vector Vd bar, the vector corresponding to the valuation associated with the divisor d, and the eigenweight lambda. So all these pairings of Vd bars with lambda should be non-negative. And this condition exactly means, so this condition, well, maybe let me turn to the left, or maybe I have some room here. So this condition exactly means that lambda sits in the cone dual to the cone spanned by all these vectors. So here C is the cone spanned by all Vd bars, where D runs over b-stable prime divisor in X, over b-stable prime divisors in X. So let me say again, so these inequalities for all D means exactly that lambda sits in the dual cone of C, of this C. Let me also add that it should be a lattice vector, of course.
Will this C is the same as the C in the theorem, right?
It will be the same as the C in the theorem, but so far we don't know it. We will check it. So far it is just a notation for this cone, for this one. Excuse me. for this one. Maybe I shall put the equality by definition sign here. So C is defined as the cone spanned by all these vectors, okay? Well, we can say more. So now we want to study the properties of this cone. We can say more. So let us consider all these divisors D, all bistable prime divisors on our affine spherical variety X. There are finitely many of them. And we can find a function, a regular function. So there exists a regular function f on X, which is non-zero, not identically zero on the whole X, and which vanishes on all these divisors. So such that f equals 0 on any D for any bistable divisor D in X. Or, which is the same, in other words, the vanishing order of f along each of these D's is strictly positive. Let me again move it. Excuse me. I don't see anything else to move, so all these dots can be removed. Yeah, so we have a function, a regular function on X with positive vanishing orders along all bistable prime divisors in X. And now you may use either the second approximation lemma or even easier, just the Lee-Colchin theorem. So by the Lee-Colchin theorem says that in any representation of a solvable group, there exists an eigenvector. Of a connected solvable group, there exists an eigenvector. And we can consider the action of the Borel subgroup B on the vanishing ideal of the union on all D's. So it is a B invariant, a B stable subspace in the coordinate space, in the coordinate algebra of X. And there exists an eigenvector in this vanishing ideal. So we may assume that this regular function f is semi-invariant. It is a B semi-invariant function corresponding to some eigenweight lambda in the weight lattice. And now these inequalities can be rewritten in terms of pairings of the weight lambda with all these vectors VD bars. So all the pairings.
Well, F lambda is the action of B on what ideal? I mean.
Let me repeat again. So let us consider the vanishing ideal of the union of all these divisors. The vanishing ideal of the union of all these divisors, this will be an ideal in this coordinate algebra. And since the divisors are B-stable, this ideal will also be a B-stable subspace in here. And there exists a B semi-invariant vector, an eigenvector, in this B-stable subspace, in the vanishing ideal of these D's. And this B semi-invariant vector can be taken for F. It will have a positive vanishing orders along all these divisors because it is in the vanishing ideal, and it will be semi-invariant. So we can find a semi-invariant function with this property. Okay? So as I said, these inequalities mean exactly that the pairings of all vectors VD bar with this weight lambda are positive for all these Ds. But now let's come back to the previous page. So we have a cone with this set of generators. And we have a linear function, a vector in the dual lattice, a linear function, which takes positive values on all these generators. This means that the cone is pointed. This implies that the cone C is pointed. So maybe it will be instructive to draw this lambda somewhere on the picture. So for instance, you may take a vector in the dual space, but anyway, somewhere here, such a vector. This will be my lambda. Such that this vector, this linear function given by this vector in the dual vector space, takes positive values on all generators of the cone C. So you consider, of course, all colors, because all colors are among these divisors, and also G-stable prime divisors, for instance, the one given by this vector. All these vectors generate the cone C, and lambda takes positive values on all these vectors. This means that the cone C lies on one side of the hyperplane defined by this vector lambda, with the perpendicular direction lambda, if you like. This means that C is pointed. Okay? So we have proven this property. We do not know yet that C is this cone, but for the cone C which we defined, we have proven this property. Let's go on.
Sorry, I have a question.
Yes.
So why there exists such an F?
The question is about something here.
No. So why we have an F so that it vanishes on all D?
I just choose a function. So the union of all D's is an affine subvariety in X. I take the vanishing ideal of this affine subvariety. A vanishing ideal is an ideal in this coordinate algebra.
Okay.
And I choose a function from this vanishing ideal.
Okay.
And I can assume this function to be B-stable by the Lie-Kolchin theorem. Okay?
Okay.
Good. Now, let's go on. Let's go further. Proceeding with the...
Sorry,
yes.
I have to ask a question. So, by the Lie-Kolchin theorem, Lie-Kolchin theorem says that an representation of a solvable Lie group always have an eigenvector, right?
Of a connected solvable algebraic group, yes. Yes.
Connected. Oh, yes.
Connected is important.
Then if we decompose the representation space into a sum of the eigenvector and another B module, then we can apply the Lie-Kolchin theorem to the other B module.
No, it is not always possible. You cannot always decompose. You have an eigenvector, but you do not always have a complementary hyperplane in this space. Which is
reductive, then we have, right?
But we apply this theorem not to a reductive group, but to a solvable group. We apply this theorem to B, to the Borel subgroup. It is not reductive.
So many Borel groups are mostly not reductive, right?
Well, almost always they are not reductive. The only reductive case is when the group G is an algebraic torus. In this case, the Borel subgroup B coincides with G, and it is reductive. It is a torus. In all other cases, a Borel subgroup in a reductive group is not reductive because it contains it contains a normal unipotent subgroup. It contains unipotent elements, and the unipotent elements.
I see. Unipotent. Yes, the element that cannot be diagonalized. Like
Yeah. Exactly. So Lie Colchin theorem guarantees that you have a B-stable line, but it does not guarantee that you have a B-stable complementary hyperplane in this line. Okay, so maybe let's go on. Let's go further. So we have proved that C is pointed. Now, let us take any vector. Let us take any vector V in the intersection of C with the valuation cone. It may happen that there are no non-zero vectors. I want to take, of course, I want to take a non-zero vector. I am not interested in zero vector. It may happen that there are no such vectors, that the cone C intersects the valuation cone only at the origin, only here. Then there is nothing to do at this step. But if you have such vectors, such non-zero vectors in the intersection of C with the valuation cone, let's take any of these vectors. Then the respective valuation V is non-negative on the coordinate algebra of X. Because the coordinate algebra of X is the direct sum of irreducible submodules corresponding to the vector to the highest weights in the dual cone. And if the pairing of V with all these weights is non-negative, so if V is in the cone C, this means that the pairing of V with all these weights is non-negative. This means that the respective G-invariant valuation takes non-negative values on each of these summands and therefore on the whole sum. So we have this. And now let us do what we already did in a different situation. Let us consider the set of those functions on which the valuation V takes positive value, strictly positive value. This will be an ideal. So let me denote it by J. Maybe again, let me turn to the next line. Let us take G. So let us, maybe it is not G, it is script I, ideal. Let us take script I, be the set of all functions regular on X on which V takes strictly positive value. And it is easy to see that it is a G-stable prime ideal. G-stable prime ideal. Some time ago, I already used this construction of a G-stable prime ideal, and I left as an exercise to you to prove that this set is indeed a G-stable prime ideal. Here, the situation is exactly the same. It is actually an easy exercise. Since it is a G-stable prime ideals, it corresponds to a certain irreducible G-stable subvariety in X, that is, to a closure of some orbit. There are finitely many G orbits in X, and their closures are all irreducible G-stable subvarieties. So this ideal I is the vanishing ideal of some orbit. And furthermore, we know that, again, it was discussed on previous lectures, that in this situation, if you have a G-invariant valuation, which is a non-negative of the coordinate. Yeah.
Y is just a G stable. I think Y is just a G stable closed variety.
No, Y is a subspace in the coordinate algebra. It is an ideal in the coordinate. Y. You are speaking about Y, not
Yes.
I, but Y.
Yes,
Y is a G stable closed irreducible subvariety because it is a prime ideal, so the respective subvariety is irreducible. Not Y.
Yes.
I mean. So this ideal I corresponds to a G stable irreducible subvariety, closed subvariety in X. But any such subvariety is an orbit closure. And the vanishing ideal of an orbit and of its closure is the same. So you can write that I is a vanishing ideal of an orbit.
Yes.
It is the same thing. Okay, so now we have the following. Again, we discussed at the previous lecture that in this situation, if you have a G invariant valuation, which is non-negative on the coordinate algebra, and it is strictly positive exactly on the vanishing ideal of an orbit, in this situation, we have a morphism from an elementary spherical variety, xv, corresponding to this G invariant valuation, to X, such that the boundary divisor d sub v.
Well, Professor, I want to ask.
Just let me finish the phrase. I just wanted to say that you in this situation you have a map from xv to X, such that the boundary divisor dv, the codimension 1 orbit in xv, maps exactly to the orbit y. So we have the situation. And this implies, again, we have discussed this at previous lectures, that this picture implies, there was a lemma about it, that the vector v then belongs to the interior of the respective cone, C sub y. Now I'm ready to answer your question, to listen to your question.
Why is the closure of a G orbit that do we use that X is spherical? I think we have.
Well, I mean, X is always spherical. I mean, this is our assumption.
Do we use the fact that X is spherical? I think it is not the case that any G variety is the closure of.
So it is in the framework of this theorem. So let X be a spherical G variety. Then if X is affine, then blah, blah, blah. X is always spherical here, of course. Okay? This was your question?
I mean, why is the closure of G orbit comes from that X is spherical? I mean,
it comes, yes, exactly. It comes from the fact that there are finitely many G orbits in X. Because X is spherical, we know that. And since there are finitely many G orbits, any G stable irreducible subvariety is a closure of one of these orbits. Yeah. There are no other G stable irreducible subvarieties except for orbit closures. Okay? More questions?
No more
for the moment. Okay. Well, so we have taken what we have done. We have taken any vector in C, which is in the valuation cone, and to this vector we associated an orbit in X, such that this vector V belongs to the interior, to the relative interior of the respective colored cone corresponding to this orbit. This is what we have did right now. Now, let us take a vector, let us take a function. Well, maybe I should turn to the next page. Let us take a function. So there exists a function f, which is regular on X, which does not vanish at the orbit Y, so it does not belong to the ideal, but it vanishes on all divisors on all b-stable divisors not containing y. So imagine the picture. You have an orbit y in X, and you have some other b-stable divisors which do not contain this orbit. Then you can pick a regular function which vanishes on all these divisors, but does not vanish on the orbit. Well, because this orbit, or maybe better to say the orbit closure, y bar, and the union of these divisors d, which do not contain y or y bar, are two different affine algebraic subvarieties, closed algebraic subvarieties, the one not contained in the closure of another one. So their vanishing ideals have the same property. The vanishing ideal of the union of this divisor, of these divisors. Yes.
So sorry, I have to ask, why do we have xv embedded into x?
I did not say that. It is not an embedding. It is just a map.
Map to, yes.
Some kind of blow down map. So this map from here to here blows this divisor down to the orbit y. It is not an embedding. So it is a birational map, of course. On the open orbit, it is an identity map.
So how do we construct this map? I mean.
Well, I mean, this was discussed on previous lectures. We had a lemma about this situation.
By blow up?
No. It is here we do not construct this map. We have started with some v, and we claim that such a map exists. Well, I mean, just by taking how to say. We have considered an open B chart intersecting y, and we have said that any function regular on this open B chart has no poles along dv, and so this function is extendable on the whole as a regular function on the whole xv, and so on. This was a lemma, maybe not on the last lecture, but on the one but last lecture. Just check the proof. The proof was there. I'm afraid I have no time to come back to the proof because I want to prove this theorem. So, we have this picture, and we can pick such a function f, which vanishes on all these divisors not containing y, but does not vanish on y, not belongs to this ideal, the vanishing ideal of y. And by the second approximation lemma, which we frequently use, as you observed, we may assume that f is B semi-invariant. That f be well, maybe not with lambda. Lambda was previously used of some eigenweight mu. We may assume that f is B semi-invariant because the condition that f does not belong to this ideal means that the value of v on f is equal to zero. And now we may use the second approximation lemma. We may replace f with a B semi-invariant function with the same value of v. So v will be still equal to 0 on this function. And the values, the orders along other divisors, along these divisors, can only increase. So this function vanished on these. This means that the vanishing orders were positive. And for this function, they may only increase. So they will still remain positive. So second approximation lemma implies that we may assume in this statement that f is semi-invariant. But this means, actually, this means that mu belongs to the dual of the cone C, because the pairing of the weight mu with the vectors vd bars corresponding to these divisors is strictly positive. And the pairing of mu corresponding to the divisors containing y, these pairings are zero, because f does not vanish on y, and therefore it does not vanish on any divisor containing y. Okay? This means that all these pairings are at least non-negative. Therefore, mu is in the dual cone. And even more, we can say even more. I just have said that the pairing of v with mu is zero, because f does not belong to this ideal. And this implies that the pairing of the whole cone C sub y with mu is zero, because the vector v sits in the relative interior of C sub y. So we have this property, and also we have the property that the pairing of vd bar with mu is strictly positive for any divisor d of this type, for any bistable divisor not containing y. So all these properties say exactly that the kernel, well, that all these properties say exactly that this weight mu is a supporting function for the face of C containing the vector v. So the picture, again, coming back to this page, the picture is like this. So you have this vector mu in the dual vector space. Maybe it's better to mark it by yellow, because it will be the supporting function. So we have this vector mu in the dual vector space. Which is the supporting linear function for the face of C, marked by yellow, this face, containing the vector v in its interior. So the vector v will be somewhere here. Let me draw it somewhere here. Not like this, but thinner. But maybe let it be this one. This will be my vector v. It sits in the relative interior of some face of C marked by yellow, and mu is exactly the supporting linear function for this face. And also you see that the vectors vd bar belong to this face if and only if the respective divisor contains y. So for those divisors which do not contain y, they do not belong to this face. This pairing is positive. And for those vectors which contain y, the respective vectors sit in this cone, and here the pairing is zero. So in other words, we have proved, hence, the colored cone corresponding to the orbit y is exactly a face of C, whose relative interior, as I said before, contains y. So the face, because such a face is unique. The face of C, whose relative interior whose relative interior contains V. And the set of colors corresponding to this orbit is exactly the set of colors such that the respective vectors belong to this face. So we have proved this condition, and we have proved that for any orbit in Y, this will be the face. This will be a face of C whose relative interior intersects with V, not for a closed orbit, but for any orbit. And for the closed orbit, I claim that this will be the largest face. First, I have to explain why such a largest face exists. This is easy. So there exists largest face say C max in C, whose relative interior intersects the valuation column. Well, indeed, why so? If you have two faces with this property, say C prime, C double prime faces with relative interiors intersecting the valuation column, then we may choose a vectors in this intersection. So say V prime sitting in the relative interior of this, and V double prime sitting in the relative interior of this. Then the sum of these two vectors will belong, again, both vectors belong to C, so the sum of these vectors also belongs to C. And it sits in the relative interior of a unique face of C. So there exists a face C triple prime, such that the vector V is contained in its relative interior. So for some face C triple prime of C. And obviously, this face contains both C prime and C double prime. Because if you take any supporting function for this face, C triple prime, then this supporting function will take 0 value on V. And since it is a supporting function, it takes non-negative values on V prime and V double prime. So these values should also be 0. And therefore, since V prime sits in the relative interior of this guy, of this face, and V double prime sits in the relative interior of this guy, so the any supporting function of C triple prime will vanish on these two faces. This means that these two faces are contained in this one. So we have proved that there exists the largest one among such faces.
Professor, I have many questions. Sorry, there is little time left.
Okay. Well, maybe let me just finish the first part of the proof. I have just a few words to say about the first part of the proof, and then you can ask your questions. Okay? Is it okay for you?
Yes, yes.
Okay, so now let's take this biggest face such that its relative interior intersects V. And then, as we explained before, as we explained here, to this face there corresponds an orbit. So this face, let me write somewhere here, maybe on the next page. It's better to write it on the next page. Then this C max corresponds to some orbit, which I still denote by Y. which will be the smallest orbit, because you remember the closure ordering on the orbits corresponds to the inverse inclusion of colored cones. Yeah, this we have proved some time ago. And since this C max is the largest phase whose interior intersects with the valuation cone, then the orbit corresponding to this largest phase will be the smallest orbit in X. That is the orbit which is contained in the closure of any other orbit. So this Y will be the unique closed orbit. Unique closed orbit. Okay? And we have proved, therefore, by the way, we have proved that X is simple. It contains a unique closed orbit. And the colored cone for this closed orbit will be the largest phase of C with the relative interior intersecting V. So we have proved this property. We have proved this property. We have proved this property. And we also have proved this property. Because this vectors VD bar, so we have chosen lambda somewhere here. We have chosen lambda, which takes positive values, positive pairing with all VD bars for all B-stable divisors, including all colors. In particular, all these VD bars are non-zero. So we have proved almost everything except that the cone C is spanned by CY and VD bars. But this is easy because let me say the last word. Because for any G-stable, divisor D in X, since X is simple, we already proved it, this divisor should contain Y. And this means that VD bar belongs to the cone C sub Y. And this means that the cone C, so the cone C, let me recall by definition, the cone C was spanned by all vectors VD bar corresponding to all B-stable divisors, including colors and including G-stable divisors. So the colors are already in the set of generators, and if you add G-stable divisors, then in particular you get the whole this cone, all vectors in this cone. So this implies that actually the cone C coincides with the cone spanned by all vectors in C sub Y and all colors, and all vectors corresponding to colors. And finally, we have got this equality. So this C, which we defined here in this way, is exactly this cone. So we have proved all these 5 conditions. I have finished the implication from the left to the right in the proof. And I have to answer your questions, as I promised.
I want to see the second last page. I did not look at proof carefully.
Okay.
So CY is a space because it's pairing with mu is 0, right? It is.
Yeah, and also because mu is in the dual cone. So the pairing of mu with all vectors from C is non-negative. And the pairing of mu with V is 0 and V is in the interior of this phase. So
what V is it? V is in the interior. Yes, I see. I mean, although we have that the pairing of Cy and mu is 0, did we prove that all things pairing with mu that are 0 is in Cy? Do we prove this?
Well, I mean, what is Cy?
Yes, we prove that we use the condition that VD bar mu, the pairing of VD bar and mu is positive when D does not contain Y.
Yes. So this Cy is generated by all vectors corresponding to VD bars such that D contains Y. All these vectors are in C, of course, but not all vectors generating C are in this set. So Cy is spanned by those generators of C, which correspond to the divisors containing Y. And since mu takes non-negative values on all these vectors and takes 0 value on V, it takes also 0 vectors on those generators which generate a cone such that V is in the relative interior of this cone. So concluding, we can say that Cy is spanned exactly by those generators of C for which we have equality here. And this means that Cy is a phase of C. Okay?
Cy is generated by these equality and inequality. Yes, I see.
Okay. Well, more questions? Well, actually, it's a pity that I didn't manage to finish the proof because on the next lecture I have to come back to to the formulation of this theorem and to recall what we had here to prove the reverse implication. Yeah. I know
that the sum of two interior vector is in the interior, and so how can we conclude that the C triple prime contains the C prime? C double?
You are discussing this issue, yeah?
Yes.
So we have a vector V prime in the relative interior of this guy. We have vector V double prime in the relative interior of this guy. These are faces.
Yes.
And their sum will belong to C, first of all, right?
Yes.
Because this is in here, this is in here, and their sum will be in here.
Yes.
Since V belongs to C, there exists a unique phase of C such that V belongs to its relative interior.
Yes.
Right? Okay.
Yes.
So we have this phase C triple prime. Now, let's take a supporting function for this phase.
Supporting function.
It takes a 0 value. It is a linear function which takes 0 value on this phase and positive value outside this phase on this cone. Okay?
Yes, I see.
Okay. Then this function takes 0 value on V. And it takes either positive or 0 values on here.
Oh, so he must take 0 values on both of them. So
exactly. It must have take 0 values, and therefore it takes 0 values also on these faces. Because these guys are in the interior. And we have a supporting function. So we have a function which is non-negative on C. It takes 0 value somewhere in the relative interior of C prime, then it has to take 0 value on the whole C prime.
I was thinking about when V prime approaching the original point, then V approaching V double prime. I was thinking about something like this, but the correct formulation is using the supporting function.
Yes. It is better to explain this with supporting functions. Okay, so more questions?
So the last page, I want to see some. I want to have a screenshot. Yes, thanks.
Okay. By the way, the notes appear always on the disk, so you even need not make screenshots because everything will be visible in the PDF file maybe a day later or so. But of course, you may take screenshots as well. So, more questions? Well, you see that there is a lot of convex geometry in the proof. So this convex geometry is quite easy. So you always have to keep such kind of pictures in mind to check the arguments. But of course, you need some skill to operate with convex geometric things. So maybe it is not that easy for the first glance. But I assure you that essentially these arguments are easy, not complicated. So I still have to prove the reverse implication. I wanted to do it on this lecture, but I spent some time answering questions, which is always good to have questions and answer them. I hope this clarified things. But the disadvantage is that I have to postpone the proof of the reverse implication for the next lecture. If there are no objections, because for me, I can spend another 10 minutes to explain the reverse implication, which will be shorter, but I don't want to waste your time. Maybe.
Well, you mean that the next lecture we will not talk about the reverse implication?
You mean?
Well, you mean that in the next lecture, well, about 2 weeks, 2 weeks later, we will not talk about the reverse implication.
Oh, the problem is that we have to discuss the reverse implication if you want to prove the whole theorem, and I want to do it. Either, yeah, I mean, I think I have no choice because it's already 10 minutes after the lecture, after the end of the lecture. I don't want to take more of your time. So we have to prove. Maybe I just make a screenshot of the formulation of the theorem, and we'll prove the reverse implication, I hope, in 10 minutes or so, because it is shorter than this direction.
Yes, I see. Thanks. In the next lecture, right?
Yeah. So let me recall, as you already noted, that let me maybe put it in the chat to memorize for everyone. That sorry. That the next lecture will be on Monday, the 8th of May, because of holidays. And if you have no more questions, we can finish now. If you still have questions, then I'm still ready to answer your questions. More questions so far? As I usually say, if you will have questions later, do not hesitate to write me. I will answer all questions. By the way, I apologize to Lian. He wrote me something, some question about an exercise. I didn't have time to answer this question yesterday. I will answer your question today in the evening.
No problem. Thanks.
Yeah. I just wanted to say that I observed your question and I read it and I will answer quite
Okay,
soon.
no problem. Thanks.
Yeah. So, and I invite everyone to write me if you have questions. Okay. So shall we stop at this point? Let me stop sharing then. And I say goodbye to all of you. I wish you nice holidays on the next week, and see you in 1 week and a half on next Monday, on May the 8th. Okay. Bye.